Good morning, everyone. My name is Engineer Ryan Poldi Bulide, and I will be your new instructor for this subject. We have Advanced Structural Design. Now, I do know from your previous instructor, we have Engineer Benito Garwagueo. He was able to introduce already this subject and at the same time discuss with you the concept now of plastic design and analysis concept. So for today, before we advance now to our next topic, which is composite beams of concrete slab and structural steel, I would like for us to recall first some of the concept now of plastic design, all right, by solving one of the problems now which is included on your plate. So before we proceed there, I would like for us to discuss first the school calendar now, which is provided by the university for the second trimester of academic year 2020 and 2021. Right, so this is very important for you to know. That is because for the second trimester, which began at January 7 and will end on April 15, 2021, the first half now is from January 7 up until February 2022. Now do take note that our subject belongs on the first half. So for the first half, midterm examinations for all subjects under the first half will be on January 28, 29, and then 30. And then for your final examination for subjects under the first half, we have February 19, 20, and then 22. So do take note that for this subject, for our subject, your midterm exam now will be on January 28. January 28, which means we only have four meetings left before your midterm examination. All right? And then for your final examination, we will be having your final examination on February 22. So for our finals, we will be having 7 meetings. So these meetings for midterm examination, 4 meetings, final examination, 7 meetings, those includes now the exam itself, examination day itself. So we have to fast track our discussions. Nonetheless, of course, I will be doing my best to impart with you now the concept of advanced structural design. All right, so for the second half, that will begin on February 23, then end on April 15, 2021. So that is the school calendar now for the second trimester of academic year 2020 and 2021. All right, so let us now proceed to our discussion. So for our discussion today, I have listed here some of the topic learning outcomes, wherein by the end of this lecture, the students should be able to, I have here the first one, the first topic learning outcome would be identify the plastic moment and elastic moment of symmetric and non-symmetric eye-shaped section. So I do know that some of you were already familiar with this concept since I was browsing through your plates that you have submitted. Some of you were able to properly execute now on how to properly determine the plastic moment and then the elastic moment. Some of you committed some mistakes, small mistakes, which led to a wrong computation. All right, so the next topic learning outcome, we have properly determine the shape factor of a section. And then the last one we have here, for you to grasp now the idea of composite beams of concrete slab and structural steel. That is because for today, I will be introducing now to you the concept of composite beams of concrete slab and structural steel, and then we will be supplementing it next meeting. All right, so next slide. All right, so for our first order of business, that is for us to recall now your discussion with Engineer Garwagueo. All right, so I do know that he was able to upload now a module which properly defines now plastic design and analysis concept. Now, For our first discussion, let us try to recall first on how to properly determine the plastic moment, elastic moment, and then shape factor of either a symmetrical or unsymmetrical I-shaped section. So how do we do that? I have listed here a summary of equation for these three conditions. For your plastic moment, we have MP is equal to Fyz. Elastic moment, M is equal to Fy multiplied that by S. For your shape factor, that is just your plastic moment divided by your elastic moment. Now, some of you might be wondering now that I have utilized here different representations now in computing for our plastic moment and elastic moment. Though you can still utilize the representations which you are accustomed to, I am very adaptable on how you are going to compute now your on how you are going to compute these quantities. However, you must make sure now that your computations is correct. All right, so for plastic moment, MP, Fy here now is your allowable stress. Z here now, we are going to compute this one. Say for example, let us show it utilizing this problem. All right, so for your elastic moment, we have Fy multiplied that by S. Wherein S here now, we are going to show it later on how you are going to compute this one. And then for the shape factor, since that is the plastic moment divided by the elastic moment, we can cancel out Fy and Fy there. So shape factor now can also be represented as Z all over S. All right, so let us proceed now to this problem. Take note that this problem was on your plate number 101, specifically problem number 2. It says here on the problem that the allowable stress now for this I section is 230 MPa. So we are to determine now the following. Number 1 is the elastic moment with corresponding sketch of the top and bottom stresses. Number 2, we are to determine the plastic moment. And then number 3, we are to determine the shape factor now of this section. So do take note now that the problem given here is a symmetrical section. So computation for symmetrical and unsymmetrical are quite similar, but for unsymmetrical section, there will be differences now when you are computing for the moment of inertia. Then at the same time, of course, when you are computing for the value for phi. All right. So say for example, let us determine first the plastic moment now for this equation. Now since this is a symmetrical section, if I were to cut this in half, right here, if I were to cut this quantity now in half, I will have here equal values, which is 250 divided by 2, so I will have there 125. So this is now 125 mm. Then I also have here 125 mm. So if I were to denote the top part now as area 1 and then the bottom part as area 2, now since this is a symmetrical section, we can therefore conclude that area 1 now is equal with area 2. So if this is a symmetrical section, we can denote area 1 as equal with area 2. But if it is, or if the problem is an unsymmetrical I section, area 1 now is not equal with area 2. Alright, so after this one, our next step is for us to determine now the value for y. So say for example, let us consider area 1. Take note that area 1, let us first determine the value for area 1. So for us to be able to determine the value of area 1, what are we going to do? I need the length now of this part. So if I were to determine the length now of this part, that is just 125 mm minus 20 mm. So I will have here, this part now is 105 mm. All right, so solve for area 1. area 1 now is equal to, I will have here 20 times 200 plus, I have there 10 mm, multiply this by 105 mm. The value for area 1, which is also the same as the value for area 2, is now equal to, input that on your calculators, 200 times 20 plus 10 times 105. So we have here 5050 mm. So this is now 5050 mm. All right. So for the next step, that is for us to compute now for the value for y. Now, since this is area 1, we are considering this one as area 1. What are we going to do? We are to utilize now Varignon's theorem for us to be able to determine the value for y. All right, so say for example, y now will start here. So let us denote y in there. So I have here y1. Of course, if this is an unsymmetrical section, the value of y1 now will differ with the value of y2 here at the bottom part now of your section. Now, since this is a symmetrical section again, y1 will be equal with y2. So, let us utilize Varignon's theorem. I have here Varignon's theorem to solve for the value of y. Now, I do know from your plate that you utilize equation based for you to be able to determine the value for y, which is also correct. So for Varignon's theorem, I will have here area 1 multiply this by y1 is equal to the area now of the first part, which is this one. I have there 20 times 200, multiply this one by, from the centroid now of this part up until here. So what is that distance? I will have there 125 now minus 10, so I will have there 115. So I have here 115 plus the second part now of our diagram for area 1, I have this part. All right, so that is 10 times, I have here 105, multiply this one by the centroid now of this part up until the center of our diagram, that is 105 divided by 2, which will give me 52.5. I have here 52.5. So divide both sides by area 1, and then I have here area 1, which is equal to 5050. Area 1 will cancel out. Therefore, y1 now is equal to, input that on your calculators. I will have there 20 times 200 times 115 plus 10 times 105 times 52.5. Divide this by 50, which will now give me 102. The value for y1 now is 102.00005 mm. So we were able to determine now the value of y1. All right, the next step now is for us to determine from our equation, plastic moment now is equal to, that is Fy, which is your allowable stress, times Z. So how do we compute for Z? That is just Z now is equal to area 1 y1 plus area 2 y2. Now, since this is a symmetrical section, I can just compute for area 1 y1 and then multiply it by 2. But if it is an unsymmetrical section, you need to determine the value for all of these quantities. All right, so what will happen now? Z now is equal to what is area 1, that is 550 mm, multiply that by 102.005, sorry, this is millimeter squared. So that is now 102.005 plus area 1 and y1 is the same as area 2 and y2. So let me write it here. 550 multiply this by 102.005. The value for Z now is equal to, I have here 550 times 102.005. This is now equal to, Z now is 103,250.5. So let me check, 103,250.50. This is now millimeter cube. So if we are trying to solve for the plastic moment, MP now is equal to, the allowable stress according to the problem is 230 megapascal. So this is sorry, I have here 230 MPa, multiply this one by 103,250.50 millimeter cube. Plastic moment now is equal to, I have here 230 times 103,250.50, 103,250.50, which will now give me plastic moment, which is 236,957,615. This is now Newton millimeter. All right, so that is 236,957,615. Or we can also write this one as 236.96 kilonewton meter. Take note, your allowable stress is in megapascal, or that is Newton millimeter squared. Multiply that to millimeter cube, giving us Newton millimeter. Converting that to kilonewton meter, I have here 236.96 as the value now for our plastic moment. All right, so proceeding now to the next one, I have here, we have to determine the elastic moment. So for the elastic moment, our equation now is, I have here M is equal to Fy multiplied that by S. Wherein what is S? S is equal to I, or your moment of inertia, divided by Y max. Now what is Y max? Y max now, since this is a symmetrical section, if I were to divide this by 2, the value here now is equal to, I have here 125 mm, and then this is also 125 mm. So Y max here now is 125 mm itself. Now, if this is an unsymmetrical section, you need to determine the location now of your neutral axis. So either by utilizing your Varignon's theorem, you can determine the location of your neutral axis. And then substitute now whichever is whichever has a higher value, be it either on the top part or at the bottom part of your neutral axis. Same here, this is now your neutral axis. All right, so for elastic moment, we already have your y max, which is equal to 125. If this is a symmetrical section. I repeat, for unsymmetrical section, you need to determine now the location of your neutral axis, either by utilizing now your Varignon's theorem, and then determine which of those two, either the top part or the lower part now of your I section, will be the value now for your y max. Alright, so next order of business is for us to determine now your moment of inertia. For your moment of inertia, if this is a rectangular section, the easiest way to compute now, easiest way for us to compute is for us to consider the diagram as a whole. But say for example, let us try to recall first the equation now for moment of inertia of a rectangular section. So that is 1 all over 12 bh cube, add this by the area, and then d squared. Alright? Now, as I have said, if this is a symmetrical section, the easiest way for us to determine now the moment of inertia for this section is consider the section as a whole. So I will consider this section, this rectangle as a whole, and then subtract these two rectangles. I have here these two rectangles. Since this is symmetrical section. So what will happen? I now is equal to 1 all over 12, the base, which is still 200 mm, and then the height, which is 250 raised to 3. Now take note that since I considered the whole figure, what will happen now to this part? Since the whole figure is resting on the neutral axis, AD squared now can be cancelled out. That is if you are considering the whole diagram. But if what you did for the computation now of your moment of inertia is to consider this part, and then consider this part, and then this part, then you have to consider AD squared. All right? So if I were, since I considered the whole diagram, I need to subtract this part. All right? So this is now minus, I will have here 2 multiply that by 1 all over 12. Take note that this one is symmetrical now with this part. So I will have here the base now, compute for the base. So that is 200 minus 10, subtract the width now of this part, and then divide this by 2. So I have here 95, which is our base, and then multiply this by the height, which is 250 minus 40, 210 cube. The value for I now is equal to, substitute that on our calculator, 1 all over 12 times 200 times 250 raised to 3 minus, I have there 2 all over 12 times 95 times 210 raised to 3. So I have here the value for I now, which is equal to 1137, 841, millimeter raised to 4. So I have here 1137, 841, millimeter raised to 4. So the value of S now is equal to 1137,841,66.7 divided by Y max, which is equal to 125 S now is equal to, I have here 910,273.33 millimeter cube. So let me check, 910,273.33 millimeter cube. All right, so if that's the case, if we are to solve now for the plastic moment, M now is equal to Fy multiplied that by S. Our allowable stress is, what's that now? 230 MPa. So I have here 230, multiply this by 910,273.33 millimeter cube, wherein, I'm sorry, all right, so I will have here M, which is equal to 230, multiply this by 102, 910273.33. All right, so M now is equal to, multiply this by 230, I will have here 209362866.7. This is now in Newton millimeter. So let us check, that is 230 times 910273.33. That is 209,362.86. 866.7. All right, so I have here now the value for our elastic moment. So from here, we can now determine the shape factor. Now, some of you might be wondering, you might have a different result if you are to utilize this one, 910,273.33. What I did was to consider now the whole decimal places for us to have a more accurate answer. So I utilize here 0.3333 and so on, which gave me an answer which is 209,362,866.7. But if you are to utilize two decimal places, it will give us an answer which is equal to 209,362,865.9. So there is a few difference now if you are to utilize this value. But if you are to utilize the whole value now when dividing this quantity, then multiply this quantity by 230, it will give you this value. Or this is now in kilonewton meter. I have here 209.3.36. This is now kilonewton meter. So we already know the value for our plastic moment and our elastic moment. The last step now is for us to determine the shape factor. So for the shape factor, that is either we utilize now your plastic moment, which is MP, divide this by your elastic moment, which is M. Or you can also utilize, that is Z divided by S. Now since plastic moment here is Fy times Z, and then elastic moment is Fy times S, the allowable stresses now on the numerator and denominator will cancel out. So shape factor now, basing on the value for our plastic moment and elastic moment, our plastic moment has a value of 236.96, and then our elastic moment 209.36. So let us rewrite it here. I have here 236.96 all over 209.36. The value now for our shape factor for this problem is 1.1318. All right, so this is now should be your final answer for problem number 2 on the plate now given to you by Engineer Garwaguillo. So I repeat, for symmetrical I-shaped section and unsymmetrical I-shaped sections, the concept now for computation is the same. Now there will be alterations now when you compute, especially under the moment of inertia. Then at the same time, when you are going to compute now for the value for y. Now since under unsymmetrical sections, y max now is not, or the neutral axis now will not rest on the center now of our diagram. So you have to determine the position of your neutral axis when your diagram is unsymmetrical. All right, so if your answer now for problem number 2 is this one, then I can guarantee you now that you can easily understand what we are going to be discussing next. All right, so for our next topic, we have here composite beams of concrete slab and structural steel. All right, so for this one, I will be introducing it first to you, and then we will try to solve a problem now, which is connected to this problem. Now, when we say composite beams of concrete, slab, and structural steel, it says here, steel concrete composite beams consist of a steel beam over which a reinforced concrete slab is cast with shear connectors. All right, so in conventional composite construction, concrete slabs are simply rested over steel beams and supported by them. All right, so for this topic, we will be talking more about steel beams or your I sections, which is this one, wherein we have a concrete slab which will rest on top of it. So we will not be discussing yet reinforced concrete slab having shear connectors. Now when I say shear connectors, I have this one. So for this topic, we have here your steel sections connected to a reinforced concrete slab with steel connectors or shear connectors. We will be discussing it in another topic in the finals. So we have here your shear connectors, or that is your headed studs. All right, so I repeat, for this topic, we will be mainly talking about, I have it here, concrete slabs which are simply rested over steel beams. And then these steel beams support these concrete slabs. All right, these two components act independently under the action of loads because there are no connection between the concrete slab and then the steel beam. All right, so for you to properly grasp now the idea of composite beams, let us try to do this problem. So say for example, I have here another symmetrical I-beam section. So take a look at this one. So I have here a symmetrical I-shaped section having a height of 400 mm and a base of 250 mm. Thickness now of this part is similar with the thickness at the topmost part, which is 30 mm, and then the thickness here is 25 mm. Now observe now at the top part of our beam rests a concrete slab. So this is a concrete slab, say for example there. This is now our concrete slab having a dimension of 1.50 meters in length and a thickness of 150 mm. Alright, so say for example this is our diagram. And some of the given here now, we have here n is equal to 8, Fy and then Fc prime. Now you might be wondering, what is this n and then what is this Fy and Fc prime? So this Fy and Fc prime are utilized for us to check if the allowable stresses that we were able to compute now basing on this diagram are safe. Then at the same time, N here now is what we call as the modular ratio. That is because we cannot compute immediately for the stresses now. We cannot compute immediately for the stresses of this diagram, considering that this is a concrete now and this is a steel I-beam. Right? So what are we going to do is for us to convert now or to transform the value of this concrete slab into steel. And how are we going to do that? We are to utilize now the modular ratio. It says here, the modular ratio n is divided into the width dimension parallel to the neutral axis of the concrete section being transformed to find an area of steel that has an equivalent axial stiffness of the concrete. All right? So it says here, we are going to divide now, we are going to divide the width of the concrete slab by the modular ratio for us to have an area of steel which has an equivalent axial stiffness of the concrete slab. So what will happen to our diagram? I have it here. For our modular ratio, this is the untransformed section. Untransformed because this is still our concrete slab. Now, what happens if we transformed it now to our to steel? I will have it here. This is now the length divided by the modular ratio. So this is now our transformed section, which we are going to utilize now in computation for this problem. Okay, so that is for composite beams of concrete slab and structural steel. Okay, so let us go back with this problem. So what is being asked for us to determine in this problem? For this problem, it is asking us to determine now the stress at the bottom part of the beam, which is here, at the topmost part of the beam, and then at the interface now between the concrete slab and then the beam itself. So how are we going to do that? The first step is for us to transform first the concrete slab into a steel. All right, so how are we going to do that? Utilizing now the modular ratio. So say for example, let us start our computation here. So I will have here transforming this part, which is our concrete slab into a steel. So I will have there, let us denote it as BE. So let us denote this one as BE now. BE will therefore be 1500 mm divided by 8. I will now have here, that is now 1500 divided by 8, 187.5. I have here 187.50 mm. Therefore, the length now of the steel section on top of the I-beam here now is 187.50 mm. Still having the same thickness, which is 150 mm. Alright, what is the next step for us to be able to determine the transformed moment of inertia? Now, when we say transformed moment of inertia, we are to determine the moment of inertia of the transformed section. And how are we going to do that? We have to first identify the location of our neutral axis. And how are we going to do that? Utilizing your Varignon's theorem. But before we proceed that, for easier computation, let us determine first the area now of each of these sections. Right, so say for example, let us do it here. Area 1 now is equal to the top part first. I will have here 187.50, multiply this by 150, I will have here 187.50 times 150. I have there 28125 millimeter squared. All right, next one, area 2. Let us do from top to bottom. So I will have there 30, multiply this by 250. I will have here 7,500. And then area 3, our vertical section, that is now 25, multiply it by 400 minus 60, I will have there 340, which will therefore give me 8,500. And then the last part, area 4, is the same as area 2. So that is 30 times 250, which will also give me 7,500. All right, so for us to be able to determine now uh, the location of our neutral axis, say for example, I will apply here Varignon's theorem. So how are we going to apply Varignon's theorem? Say for example, let us denote here area total. Will be basing first our computation of y from the top. So I will have here multiply this by y top and then equate it to the area of each of this section and then the distance of their centroid to the top part now of the steel section here. All right. So what will happen now? I will have here area 1, which is 28125, multiply this by the distance of its centroid to the top, that is 150 divided by 2, which is equal to 75. Next, I have there 7,500, multiply it by the distance of its centroid here, centroid to the top part. So that is 150 plus 30 divided by 2. I have here 165. 165 mm. Then the next part, that is now the area of this section, which is 8,500. 8,500, multiply it by its centroid, the distance of its centroid to the top part now, which is 150 plus, that is now 200, which will give me 350. So I have here 350 mm. Sorry, 350 mm. And then the last part, 7,500, multiply that by, so that is now 150 plus, that is, say for example, that is 400 minus 15, which will give me 535. So this is now 535 mm. I repeat, how did I where did I get 75 mm, 165 mm, 350 mm, and then 535 mm? That is now the centroid or the distance of the centroid of each section to the top. Since I am trying to determine now the location of the neutral axis, basing it from the topmost part now of our diagram. So what will happen if I were to divide both sides by area total, divide both sides by area total, and then divide this one by our area total now is, take the summation of this part, so I will have there 28125 plus 7,500 plus 8,500 and then 7,500, that is now 51,000. I have here 51,625 millimeter squared. So this is 51625. Area at the top our area total and area total will cancel at this part. Therefore, y top now is equal to, substitute all of this on our calculator, then I will have here 200.18 mm. Alright, so this means that the location of our neutral axis is 200.18 mm from the top now of our diagram. So try to locate now where 200.18 is. So 150 plus 30, that is 180. So approximately, I will have it here. So I have here now the location of our neutral axis. This is now y top, which is equal to 200.18 mm, and then this will now be y bottom. Let us denote this one as yb. So how are we going to compute for y bottom? That is just 400 plus 150, subtract it by the value of y top, which is 200.18. Therefore, I will have here 349.82 mm. Alright, so we already know the location of our neutral axis, the total area, and then we were able to transform our section from a concrete slab to a steel section. Now we are now ready to determine the moment of inertia. Right? Do not forget Varignon's theorem. So for us to be able to determine the moment of inertia, so I have here for I, kindly disregard this one. Kindly disregard that one. So for I, how are we going to compute that one? Since we are considering a rectangular section, I now will be 1 all over 12 base times height cube plus the area of the section, and then d squared. What is d squared? That is the distance of the centroid now of that section from the neutral axis. So say for example, let us start off with the steel section muna. I now is equal to 1 all over 12. The base now of the steel section is, going back here, the base is 187.5 and then a height of 150. So we will have here 187.50 times a height of 150 cube plus the area, which is equal to 28125. This is the area of the steel section, times what is its distance, the distance of its centroid from the neutral axis. So the distance of its centroid from the neutral axis, that is just 200.18 minus, that is 150 divided by 2. Take note, centroid is at this part, so that is 150 divided by 2. Then subtract that value from 200.18. That is now equal to 125.18, right? So I have here 125.18 squared. So that is for the steel section. Alright, let us proceed to the top part now of our I-beam. So add this one, so this will become plus 1 all over 12, multiply this by, the base now is 250 times a height of 30 mm, raise this to 3, plus, what is the area? That is now 7,500, and then the distance of its centroid from the neutral axis, that is, I will have here 200.18 minus, subtract 150 mm. 150 minus, that is 30 divided by 2. So I will have there 35.18 as the distance of this section from the neutral axis. All right, so we have here 35.18 squared. And then the next one, let us try to determine this part. All right, so what will happen there? Still the same, I will have here 1 all over 12, multiply this one by its base, which is 25 mm, the thickness, times the height, which is 340 mm raised that to 3, its area, which is 8,500, multiply it by the distance of its centroid from the neutral axis. So are we going to do that? Take note that if I were to divide this by 2, so 340 divided by 2 is 170. So the distance now from this section, the distance from this section up until here is 170 mm. So I need to determine this distance. And how will I do that? That is just 349.82, which is YB, minus, I need to subtract 30 and then minus 170. So I will have here 149.82. So I will have here 149.82 squared. And then the last part now, the bottom part of our I section, 1 all over 12, same as this part, that is 250 as its base, multiply it by 30 cube, plus 7,500, which is its area, times the distance of its centroid from the neutral axis, that is now 349.82 minus, that is 30 divided by 2, which will give me 334. I have here 334.82 squared. All right, so input all of that on your calculator, wherein the resulting value of I now would be approximately, I have here 1617.32 multiplied by 10 raised to 6 millimeter raised to 4. All right, so the value for I now, or the transformed moment of inertia, is 1617.32 times 10 raised to 6 millimeter raised to 4. All right, now that we know the transformed moment of inertia, we can now proceed to the next step. According here, we have here conditions provided. If M now is equal to 500 kilonewton per meter, we are now to determine the stress at the bottom of the beam, at the interface, and then the topmost part of the beam. And how are we going to do that? So take note, M here now is the moment now which is provided for our steel section. That is 500 kilonewton per meter. Say for example, let us start off at the bottom or the stress at the bottom of the beam. So for the stress at the bottom of the beam, we are to utilize this equation. So say for example, let us denote this one as FSI, which is equal to the moment multiply this by YB all over our transformed moment of inertia. But take note, our M here is in kilonewton per meter. So I will have here 500 times 10 raised to 6. This will now become in megapascal. Multiply this by YB, or the distance of our neutral axis from the bottom, which is 349.82 divided by our transform moment of inertia, which is 1617.32 times 10 raised to 6, FSI now will be equal to, I have here 108.15 megapascal. Alright? So for letter B, it is asking us to determine now the stress at the interface of the diagram which is provided. So how are we going to do that? There are two options here. The first one is for us to determine the steel interface. Determine first the steel interface, and then after determining the steel interface, we are to determine the concrete interface. So I have here steel interface first. For the steel interface, what will happen there? I will have here Fi, which is F sub I S. What will happen there? Same process, that is now moment, multiply this by y all over I. Wherein the moment now is 500 times 10 raised to 6. Multiply this by, what will be the value of y? The value of y now will be the centroid now, this one, the centroid of our steel section up until the neutral axis. So take note, that is 200.18 minus 150. Oh, I'm sorry. That is supposed to be, the value of y now will be from the interface of the steel section and then our I-beam to the neutral axis. I repeat, the value for y now for the steel interface would be the distance now from the bottom of the steel section to our neutral axis. So that is 200.18 minus 150 mm, which will give me, I have here 50.18. So I have there 50.18. Divide this by the transform moment of inertia, which is 1617.32 times 10 raised to 6. The stress now for the steel interface is equal to, I have here 15.51 megapascal. Right, so let us check. That is 500 times 10 raised to 6 times 50.18 divided by 1617.32 times 10 raised to 6. That is 15.51 megapascal. And then the next step is for your concrete interface. Since our original problem is a concrete slab, so what will happen, or how are we going to compute for the concrete interface? That is utilizing again the modular ratio. So that is, let us denote this one as Fi sub C. That is now utilizing the steel interface, which is 15.51. So we will have here 15.51 megapascal. Divide this one by the modular ratio, which is 8. So I will have here 15.51 divided by 8 now is 1.94 megapascal. So we already have here your steel interface and then the concrete interface. And then the last one, we have your topmost part now of our diagram. What will happen there? So I will have here FST, the stress now at the top part, the same My top all over I. So instead of using Y bottom, let us utilize Y top. So I will have here 500 times 10 raised to 6. Multiply this by, the value for Y top is 200.18 all over, that is 1617.32 times 10 raised to 6. So the value now for the stress at the top is equal to 7.74 megapascal. Alright, so these are now the stresses. At the bottom of the beam, we have 108.15 megapascal. At the interface, we have your steel interface and then the concrete interface, and then at the topmost part now of our diagram. All right. And then the next part now, we are to check everything under allowable stresses. And how are we going to do that? Utilizing now what is given on the problem. We have here Fy, which is equal to 250 megapascal, then Fc prime, which is equal to 20 megapascal. All right. So from here, how are you going to utilize those stresses? Of course, we are to utilize the equation for allowable stresses. What are those equations? Allowable stresses. For our allowable stresses, the equations to be utilized, we have your Fc, which is equal to 0.45 Fc prime, and then Fs, which is equal to 0.60 Fy. Thus, we will have here values which are equal to Fc is equal to 0.45 times 20 is equal to 9 megapascal. And then Fs is equal to, we will have here 0.60 times 250, which is now equal to 150 megapascal. So what will now happen here is that we are going to compare these allowable stresses with the stresses that we have computed from here. All right. So how are we going to compare now? We are going to compare Fc with the value of the topmost part now of our stress. And then we are going to compare Fs with the value of the bottom part now of our beam. All right. So compare now. I have here F, what's that now? I have there FST, which is equal to 7.74 MPa, 7.74 megapascal is less than the allowable stress, which is equal to 9 megapascal. So the implication now of this one is that this part now of the beam will fail. Then the next one, FSI, which is equal to, that is 108.15, is also less than the allowable stress for Fs, which is 150 MPa. Implication here now is that this part now of the beam will also fail. So what does this mean? It means now that the beam or the I section, the steel I section, cannot support now the concrete slab which is resting on top of it. All right? So that is it for our discussion um, under composite beams of concrete slab and structural steel. So for next meeting, we will try to supplement what we have discussed today. Then at the same time, give you more activities so that I have something to record now for your midterm scores. Structure. That's it for our discussion for today. So for any inquiries or questions regarding of what we have discussed today, feel free to message me on my Outlook or UC-BCF email, which is rdbulide@uc-bcf.edu.ph. All right, so you can also utilize your Canvas for you to be able to message me regarding your inquiries. All right, so I would like you to open your Canvas from time to time since I will be posting now updates regarding our subject on our Canvas accounts. So that's it for today. Thank you very much and have a great day.